Здравствуйте, Володя.
Добрый вечер.
Нет, нет, все хорошо. Мы сейчас с вами начнем.
Да,
Э,
хорошо.
Просто пока у нас не все пришли, кто обычно ходит.
Ну, нет, мы обычно ждем минуты 3, а то и 5.
Да, да.
Так и бывает.
Привет, привет,
Привет.
Володя.
Привет. Привет. Рад видеть.
Мгм.
Ой, что-то связь сегодня не очень. Обрывалась вчера, вообще обрывалась. Я имею в виду здесь, в институте. Да.
М.
Приходил человек проверять связь. Я просто боюсь, что вот я сейчас смотрю, что я зависал.
Кстати, Володя, а как там это вот был тогда этот замечательный молодой человек, который был системным администратором в институте, всем помогал? Я помню, он там что-то болел, ему там даже какие-то деньги на
Да.
лечение собирали. Он все в порядке? Он
Ну,
работает?
я не знаю, наверное, тут они такие вообще-то очень, я бы сказал, коллаборативные, но они не все могут, наверное, потому что...
Он работает еще, этот молодой человек просто? Помню, он там
Я
был.
не знаю, про кого вы говорите, здесь есть молодой человек, который очень, очень такой
Я не
хороший.
помню, как его зовут, такой, он такой черненький такой был. Ну, не совсем черный такой, арабский такой внешности. Я уже забыл, как его зовут.
Ну, я не знаю. Нет, наверное, нет. Наверное, нет. Наверное, его нет.
Может быть, его нет. Я посмотрю, там где-то у меня в архиве есть письма, когда там собирали ему помощь. Да.
Так, я вот хочу пока проверить, подсоединяется ли мой, да или нет. Что-то не хочет. Нет, подсоединяется.
Мгм. Сейчас я Саше Жиглову напишу, чтобы, если он придет, чтобы мы его ждали. А если не придет,
Видно хорошо?
Ничего.
пока ничего не видно.
Ничего не видно? А у меня
Нет.
видно.
Ну,
Только черный экран.
А сейчас? У меня все видно, не знаю. Что себе?
я могу быстро
Так.
доехать до твоего офиса, а вот
Нет,
остальные...
сейчас опять. Опять исчез все. Опять все исчез. Сейчас опять появился. А у вас?
Нету.
Не появился. Вот Саша появился зато.
Добрый вечер.
Добрый вечер.
Это здорово, но он появляется и исчезает. Это очень плохо. Все-таки что-то у них не то происходит. Так, еще раз. Конфианс. Ну, вот сейчас видно, нет?
Вот,
Да,
вот
сейчас.
теперь видно. Теперь прекрасно видно, да. Ага.
Нет.
У нас прекрасно видно.
Хорошо. Ну, тогда скажите, если видно, я пойду начинать.
Саша, мы подождем кого-то еще. Мои, значит, Даниил сегодня не появится на некоторое время. У него там какие-то дела семейные. Там родители приезжали. Кто там еще появится, может, я не знаю из моих. Такой сложный вопрос. Вот.
Я не знаю, там еще, может быть, этот мой Павел придет. Ну, по идее, он должен. Ну, может, минуту подождать.
Ну, давайте подождем минутку.
Непонятно, что он дергается.
Попало ваш...
Опять упал.
Ну, он дергается, да, я вижу, что он дергается. Он мне все время предлагает снова подтвердить, что я доверяю своему этому. Давайте я его еще раз попробую спустить. Так, а теперь снова запустить. Кейбл. Так.
О, появилось.
Да,
Все
хорошо. Да вот, появилось. А сейчас?
видно, видно все.
Хорошо. И видно, как движется, да?
Да, все видно, что движется, да.
Хорошо.
Так, я вижу, тут есть Джинху, Саш, так что по-английски, наверное, просим Володю говорить.
Okay, okay, I'm ready.
Мгм.
I'm not very reliable with, with respect to the quality of my English, but I will try.
Don't worry. Nobody's perfect when the English language is concerned.
Yeah. Our generation usually suffers a lot
Okay.
of some. Okay.
I think we can start now. So today's is the second part of Vladimir Rubtsov talk about higher Bessel kernels and Buchstaber and Kontsevich polynomials, and also beyond. I think that today we're going to go beyond. That's
Yes,
interesting.
yes. Thank you. Thank you very much, Gosha. Thank you for your invitation, because of course the subject is too big to cover everything interesting which is beyond. Even today, it is impossible. But I will concentrate on something which we missed last time. First of all, I want to make some. So reminder is the following. We have discussed the differential equations and corresponding operators, which we call n-Bessel operators. So these operators, nth order operation, nth order operator with respect not only d over dx, but also it's a logarithmic derivative. Such equations are very, very important ingredient of so-called quantum theory of differential operators, which related to mirror symmetry on projective spaces, on flag manifolds, and this is probably beyond, I mean, this description relations with quantum cohomology. And
I'm sorry, Volodya, I missed the first part, the first talk, but why it's called Bessel, the first stupid word.
This I will explain today. This I will explain today, why it is called Bessel.
It's not similar to
It is, yes, that's what I want to precise today. In which sense it is Bessel, and why we called it n-Bessel. This I explained. And what I will not speak today, Andrei, I'm sorry, I will not speak about Buchstaber and Kontsevich polynomials mainly, because I spoke last time about it. What I will want to remind again, this beautiful property of some types of eigenfunctions for some problems, which is called multiplication kernel property. It means that if we have some set of functions, you can imagine always, you can imagine that you have some differential operator behind it, or another operator, and you have a set of eigenfunctions with eigenvalues, which I denote by lambda. Then let's suppose that taking two such functions, in one function in two different points, the product of this function can be expressed in terms of the same function in the third point z, with the so-called multiplication kernel, which plays imaginary some algebraic structure. Imagine please some algebraic structure behind it. So this kernel can be interpreted like a kind of structure constant for some algebra structure on this function. And moreover, you can even formulate it in explicit forms, but at the moment it is not important for me. What is important that this kernel, which includes in this representation, doesn't depend on the parameter, eigenvalue parameter lambda. This situation is quite common, and as I told you last time, this situation was related to some duplication theorems in the theory of hypergeometric functions. And because these hypergeometric functions can be represented solutions of differential equations, and I will show how they relate to this, what I call Bessel solution. One more correction. I will today ready to make more corrections. So one more correction I want to do this. In my talk, I spoke last time about kind of Bessel. It's better say degree, and because usually the word kind people apply to two different solutions of standard Bessel equation. One solution is analytic solution, and another solution includes logarithm. So this G new function and K new function. This is the first kind, and this is the second kind. I will not in my talk mention second kind. I will speak about first kind. I'm sorry. I will speak about first kind Bessel functions. And moreover, I will speak about modified first kind Bessel functions. And I will discuss it a little bit later. If you have this Bessel function or modified Bessel function of degree 0, it was represented by Schlafly in this beautiful product theorem. So this theorem Schlafly proved for degeneration, which he called hypergeometric degenerated function. But in the same time, this product formula was, in terms of Bessel functions, degree 0, were formulated. This is usual, it's not modified, it's usual Bessel function, was proposed by Sonin and Gegenbauer. That's what I told you last time. And this product kernel, multiplication kernel, has very nice algebraic form, very symmetric and very algebraic. So this, I will make some comment about it, about this kernel. Interesting probably for Andrei. I'm not sure if he is interested in scattering amplitude, but this function is very, very close to what people.
I was attracted by, well, I thought that I know what are Bessel functions, and so I was attracted to want to learn more about them. And so this formula, the last formula, is of course new for me. I never seen it before.
But the function, you know this function, this function.
Bessel function, of course, I know. Yes.
No. This one.
Well, that's a form which I met in some, well, in some other.
This is a physicist called it Galen function, triangle function.
Okay.
Do you know it?
Well, I met it in some other problems. It's something which I saw before.
In cinematic of relativistic particles, this function gives the answer for singular point locus, for so-called Landau locus, or for this dynamics. it is interesting.
It's possible. Well,
Yeah.
Anyway, I don't remember that right now.
No. It's a very special, I would say, subject which is called topological Landau singularities, and the locus of this function is the simplest.
I learned it when I was a student, and since that time I didn't know.
Yeah. And also, as I will probably not, I will not speak about this relation with number theory and this a priori demonstration of irrationality zeta function for odd integers, and his demonstration involves some recurrency conditions, and differential equation which comes from these recurrency conditions is known as a Hoyne equation, and this Hoyne equation admit this form. I speak about eigenproblem for this operator. The function f, which enters between two differentiation operators, it is a cubic function with free term equal to 0, and the solution of this eigenproblem can be represented in this multiplication form with algebraic kernel square root of pxyz, where pxyz, it's a so-called Kontsevich polynomial, which I will not discuss today, but I want to say that this function is a degeneration of this Kontsevich polynomial, so it was just a point of depart for our interest in this multiplication kernel. Okay, now I will briefly, especially for Andrei, remind also that one Bessel operator, of course, it is not a Bessel, it is just a derivation operator with x in front of d over dx. And the eigenproblem, it has a trivial solution, exponential lambda x. Then the multiplication formula gives you just a product of exponents and exposant you should add. And then this exponential of sum can be represented with a kernel of delta function type with this exponential in z, or using the Cauchy formula in this rational kernel formula. So we have very nice and simple, even in the case of one Bessel operator, very nice and simple multiplication kernel example. But much more interesting, of course, to consider the higher Bessel, what we call n. So to Bessel, this is a solution of this eigenproblem. And if you take...
It's not a standard form of Bessel equation. Well, I don't recognize...
No. It's not standard. Not standard. It's not exactly standard. For standard form, you have I sub 0. And this is what Schlafly called degeneration, hypergeometric degeneration of hypergeometric function. You see, it's a very special formula, and it has very nice Taylor decomposition. This function, and this is an analytic solution because this second order equation has two solutions. And if you apply to this solution what people call Frobenius method, you obtain that you have two types of series. One series is analytic series, and second series include logarithm because it's irregular. This equation has irregular singularity in infinity. Sonnen-Gegenbauer formula can be written for this special type of Bessel equation in much more simple form. First of all, I recall that I just copy pasted in my first presentation usual notation for Bessel function, but it is not completely, I would say, correct. So I denoted phi sub 2 just to stress that it is second order solution. And then I can write, I will use it later. Last time I didn't use it, but later I will use it. I can write first order equation, which annihilates my kernel 1 over square root of this nice Kalin triangle function. And then I want to say that this formula is equivalent to Sonnen-Gegenbauer if you put x, y, z and replace it by u square, v square, and w square, you obtain this degree 4, variables degree 4, and it is much more easy for factorization problem, which I described last time. Now I want to make this more precise explanation how it relates to standard Bessel equation for those who, because you know I discovered Andrei, you are a physicist and you are lucky because in Mehmat courses, in regular courses, we had no regular courses of special function, mathematical physics function. We had huge ODE and PDE courses, but at the end, I don't remember that we studied Bessel, Legendre, Laguerre, and other polynomial interesting solutions for equations with singular points. And this is a very beautiful part of mathematics of 19th century, which was probably almost for now people. I don't know if now Mehmat students study this.
In quantum mechanics, these functions appear very often. Well, Bessel functions, Laguerre functions, things like that, and quantum mechanics. Well.
Okay, so the standard Bessel equation, this one equation with parameter nu, which is complex parameter, and this you see it is not exactly what I considered before. Even if you take nu equal to 0, you have x squared here, and it is not the same differential equation from the viewpoint of solutions and singular points. As I told you, this equation has two types of two solutions. I mean, two basic solutions. One solution is a first kind Bessel function. They are regular. They are analytic series, which for any index, for any degree nu, can be written like this. So it's a new kind. It's not new kind. It's not, again, I wrote in particular. I'm sorry. It's new degree, first kind. Yes.
Can you give some reference to the some classical textbook on this subject? Because the formulas.
Of course, the best reference, of course, it's Watson treatise in Bessel function. It's a classical book in 2 volumes.
Who is the author?
Watson.
Watson. Oh, the same as Whittaker Watson, right? The same guy.
Yes.
So the formulas look perfectly beautiful, I would say. The formulas, these power series.
Yeah, and there are many beautiful formulas in this book. I enjoyed reading.
Oh, yeah.
Yes. So now we can go to modified Bessel. Modified Bessel differs from standard Bessel that we admit imaginary argument. For example, if we take standard Bessel with imaginary argument, we obtain modified Bessel with usual argument. And this is after replacement argument by 2 times square root of x, we get our desired 2 Bessel. it's our argot. I want to say, Andrei, that it's our argot to call it 2 Bessel. Real 2 Bessel, it is this one. I mean, real 2 Bessel, it is this one. G0 of x.
Volodya, I think that this equation which you written before is somehow related to the standard Bessel equation, but you didn't explain how exactly. So you should change variables somehow.
Yes, this is a change of variables is written here, and I will show it again once more.
Where it's written, the change of variables?
In the next slide.
In the next slide, okay.
Yeah. What is interesting, before I'll go to this, I want to say something interesting about this Bessel equation, which we call 2 Bessel equation. This 2 Bessel equation has the following beautiful property. The symmetric square of it satisfies to also a very nice equation. So what is the symmetric square of this equation? It is a general theorem which I knew from few papers of Chudnovsky brothers. It is not also, it is easy theorem, but it was not in any textbooks. If you have a second order differential equation, any differential equation of second order, for example, but you can generalize it, of course. Then you have solutions. That's this u of x and v of x, two solutions of this equation. Now I want to write some equation for which the product u of x and v of x of any two solutions is a solution of this equation. And the theorem says that it is always degree 3 equation, and the coefficients of this degree 3 equations can be explicitly expressed in terms of p and q and their derivatives. For example, you can make a very nice exercise and take our Bessel 2 Bessel equation, which is written in usual form like y 2 primes 1 over x 1 prime minus 1 over xy. I'm sorry for these elementary things, but probably otherwise last time I was non-understandable. So this is my p of x, and this is my q of x. And then you can compute the equation. I didn't want to write I can, but it is long how to write the coefficients of this equation y3 plus a of x plus b of x plus c of x. Why? How these coefficients expressed in terms of p and q, but it is possible to write. It is long, I don't want. And you obtain this beautiful equation. This equation annihilates the square of my Bessel solution. And I called it Clausen duplication because it is similar to what I showed you from the very beginning to this Clausen duplication formula for hypergeometric Gauss function square. This duplication formula in terms of solutions very nice and very important because we can observe that this square can be expressed in terms of the first degree solution. So it's phi2, it's my phi2, 0. This it is phi2, and this phi squared. And the kernel of this duplication. It's very nice function, 1 over square root of 1 minus 4. And I was a little bit, I was in some stupor last time because I didn't understand the question. And the question was very simple. When this series converge? Of course, this series converges not everywhere. Moreover, it has very interesting story. Let's consider our expansion. This is the usual binomial type development, and we can write this function in the following power series. So here I write x over t just because it was in my integral, in my Cauchy type integral. But in fact, it is interesting that the coefficients of this series, they call binomial central coefficients.
Mhm.
And this series, I made this very elementary second year computation, and you obtain that the series has a convergence radius, which is 1 over 4. And it is interesting that what's happened when the argument equals plus or minus 1 over 4. It means if these series are converged. And in fact, it is not so elementary. First of all, it looks that it is easy. It looks because it is easy to compute the value of such series for a very close cousin of this central binomial series, namely for so-called Catalan numbers. Catalan numbers, C sub n, they are looks very close to central binomial, but they are divided by 1 over n plus 1. And this is change drastically the situation with border behavior of this series. For those who never met Catalan numbers, I would say that in his book, very famous combinatorial expert, Stanley, he proposed 66. It was a few years ago, maybe now it's even more, 66 different appearances of these numbers in different problems. For example, you have this lattice path enumeration. It is beautiful. Everybody probably knows, but if not, I should mention it. If you take, say, a plane square, n times n, and n times n net so from 1 to n, from 0 to 1 to n. And then you take the diagonal, and you can ask, let's suppose that diagonal, it is a kind of a barrier, and there is a beetle who can walk only monotonically from low point to upper point in right. So he takes some trajectory, right, up, right, and then up, right, and then goes like this. But he can also go like that, right, up, touching diagonal, but never cross it. And the question, how many ways, how many different passes for beetle from this point to this point. And this is a C sub n. The first few, this 1, 1, 2, 5, 14, 42, etc. You can easily to compute. And of course, there is a nice integral representation for Catalan numbers. This it is also easy to check this integral, and how to relate it to our binomial central binomial. You take the integral of our generating function for central binomial from 0 to x. You obtain this easy function, and this is what we get after. It's not equal, it gives you this. So if you take integration of our series, you obtain this function, and then taking, for example, x over 4 for Catalan generating function, for this one, you usually get 2, or otherwise you can write that the sum of 2 times n, or 2 times n, n n x n n plus 1 if you take it 1 over 2 times n and take x equal to 1, you obtain 2. The question, can we use it to get the answer for this point, for this series? And the answer, it is not so easy. In fact, what we can say only, we can say that if we take these central binomial coefficients, we can make estimation of its asymptotic growth. And this asymptotic growth easily gives us that these binomial coefficients, central binomial coefficients, they are bounded by 4 to n, not times n, 4 to n, and 4 to n over 2n plus 1. And then it is easy, you can obtain from the just representation 4 to n like binomial sum on 1 plus 1, 2 times n. And then asymptotic behavior of these coefficients, you see, it is 4 to n divided by square root of Pn, and it means that our series very, very divergent, even if you divided it by this 2 to n. In contrary to what's happened with Catalan. That's why Catalan much useful than central binomial. But for Bessel story, central binomials are useful because if you divide the central binomial series over n factorial, which people who are experts in analysis, they know that this is called a Borel transform. If you take the Borel transform of this series, then you obtain exponential Bessel, exponential 2 times x, e0 of 2x. This is a very nice result. Okay, what I want to go now, I want to explain to Andrei and to other, unfortunately, second time, the relation with how this different Bessel you can obtain from one to another. It's very easy. If you take a zero index first kind Bessel, it is alternating some series, and it solves the standard Bessel equation. And you see this Bessel equation, it is different from our two Bessel. It is not our two Bessel.
There we had 1 over x, right? In that place.
Yeah,
something.
yeah. That's, we write this our Bessel, and this is this. And if we take this change of variables, that's what Andrei asked me. Then we obtain from standard Bessel, we obtain our Bessel. And sometimes this equation, which I call two Bessel, people call two Klosterman equation. The reason is it is not a big secret that this Bessel equation you can also write as a first order 2 times 2 linear system. And this 2 times 2 linear system you can interpret like a connection with singular points on P1. And it means that you have some interpretation of this equation and system. Andrei, I'm sorry, I will say something which...
No, continue, Volodya.
Probably, no, I will say something which probably is not very understandable for you.
Okay.
But it means that we have a local system with irregular and regular point on P1. This local system was introduced by Dely in his proof of Weil conjecture in mid-70s. And Dely initiated study not only Bessel, but all other connections with irregular singularities. And the analogy of these studies for finite fields, they call, so it means that analogy of this local system, they call Klosterman or Schreier sheaves, adic sheaves, which satisfy to some relations, and these relations are called exponential quadratic sum. It is very important ingredient of Langland's program for finite fields, but this is beyond. I will not speak about it more. Okay, so elementary thing is that this two Klosterman equation, it's our Bessel. It's our
Sorry.
What is the difference
could I ask
with modified? Look the difference with modified. You see? Modified equation from standard equation differs by sign. So now I explained everything with 3 different Bessel equations. Usual Bessel equation, modified Bessel equation, and Klosterman or 2 Bessel equation. And in future, I will speak about n's analog of 2 Bessel equations. So I will speak about this equation, 2 times n minus x. And this is what I call n Bessel. Okay, the next drawback of my previous talk, I didn't explain enough about generalized shift or generalized translation operators. Now I explained it. This notion was introduced by Delsart and formalized by Boris Levitan. And this is very general and abstract definition. If we have some abstract variety, x, it might be any, and we have complex valued functions on this variety. And so we have a commutative algebra A with very general properties. So it's just abstract algebra, which we should know only that this is a kind of function algebra. And then we fix a point y on the base manifold x, and say that we have some operator which acts on our algebra and depends on this y. So we have a family parameterized by points of x. We say that this family is a generalized shift operator if, first of all, it's a linear operator. It's linear. Second, there is always such a point on our base manifold that the corresponding operator is identity for any function. So it's existence of identity. Then we suppose that if we have some topology in our picture, then this operator is a continuous operator in both variables. In this variable y, which is a parameter of our family, and the variable x, when we act by operator t to y on some function at the point x, we obtain some two-variable function x and y variables. And this function should be continued in the proper topology. So it's a continuity, which people always ask. Then associativity. Associativity, it's a very natural condition. If you apply your operator, which parameterized by x to f in some point z, and then you apply another shift operator. So if you first shift by x, and then you shift by y, and then it is the same if you take first shift by y and then shift by x. You obtain the same operator for function of z. So for any, it's natural condition of associativity. And
sorry, what does this x and z mean? What do the subscripts mean?
Sorry?
In condition 4, what do these subscripts x and z mean?
No, x, y, z, they are just points.
No. I mean in subscripts. You haven't introduced subscripts in your notation before. You just wrote t.
Well, if you apply your I understand your question. If you apply your if you apply your operator to function of f of x, you should just subscribe like this.
I see. So when
it means that you shift your argument, for example, by y, and consider this like function of x. And of course, it depends on y because you shifted.
So since by condition 3 you have a function of two variables, you actually need to choose what variable you actually.
No, it is always if we have application to f of x, then subscribe low subscribe is always x, and y is a shift argument. Okay, so if we have these 4 conditions, and also sometimes we add the 5th condition, that these 2 generalized shift operators, they independent if you apply shift by x and shift by y, or if you apply shift by y or shift by x. Then we say that this family is commutative. It's commutative family. It's commutativity, but it not always we don't demand it. Okay, so if we have this, we say that we have a generalized shift operators on our function algebra A. And then the following example of this situation, it was introduced by Levitan and Delsart. Delsart introduced and proposed example of Bessel, and Levitan developed the general theory. In this approach, they consider the simplest. I will just take the simplest because it is very long story, the big books written by Levitan and other people. Let's consider as a underlying manifold or half line or a segment or the whole line. And let's consider the second order differential operators with coefficients alpha of x and beta of x, where alpha and beta are complex valued or real valued functions. And then we can define shift operator, which comes from the following Cauchy-like problem. Namely, we defined this operator like this, that shift of any function f by y, it is a solution u of xy of the following Cauchy problem. If we apply our operator in variable x, it will be the same if we apply our operator in the variable y. And our solution should satisfy the two following conditions. If we take x equal to 0, then we have f of y, where f of y it's our initial function which we want to shift. And if we take derivative of over x in the point x equal to 0, then we have f of y times some constant. So if we have this Cauchy problem, that solution of this defined correctly operator. And this situation is quite general. Let me now put a relation with what I told you about multiplication kernels last time and in the introduction. If we consider element of our Weil algebra on X, then we can consider this eigen problem, for example. Then we again repeat definition of multiplication kernel, which I described, for example, for exponentials and for second Bessel. And then the main point is I want to stress that this kernel should not depend on eigenvalue lambda. And then it is interesting consequence of this multiplicativity condition. They are very, very formal, but important consequence. Let's take the product and apply our operator to this product, and apply it by x and apply it by y. In both cases, we obtain lambda or times product. So this product of two eigenfunctions is again eigenfunction. Of course, we can also apply the formula for product and consider our multiplication. Take lambda in front of it, and then we obtain that it is our kernel applying by property of eigenfunction to operator L over Z to phi lambda Z. And it is the same like replacing this operator by dual, by conjugated operator to LZ, applying to our, so it is like a conjugation in scalar product. If you,
Sorry,
yeah,
you say conjugated operator, do you mean formal conjugation? I mean, this
formal conjugation, formal.
But this operator is actually non-bounded, it seems so.
I don't, yes, it is just duality, in formal duality with respect to this imaginary scalar product. But you can consider in each example, you can precise what Hilbert space you have, what pairing you have. For example, you can impose L2 condition, and you can then concrete kernel, concrete eigenfunctions, concrete operator L, and concrete formal duality will become non-formal. It will be really conjugated with respect to this coupling operator. Okay, now I want again to make some very quick, I would say, beyond. So now we can define generalized shift operator just this is lambda. Applying this operator to our eigenfunction phi of lambda, we obtain the product. So we having the similar problem like for multiplication problem, we can reduce this problem to the problem of eigenfunctions for this generalized shift operator. And this situation is quite general. It is not only for Bessel operators. This is what I want to tell you, that this is again some story which goes beyond the Bessel. Namely, it is probably well known for those who study the Bessel function that it is a simple example of so-called spherical functions. And go further, any spherical function can be interpreted like a kind of character. And this character can be computed like a Fourier transform of some, in the case of Bessel, it is rotation or rotation invariant spherical measure. And then being character, we have a formula of products for characters for some special object which is known under the name hypergroups, and this object appeared in the Gelfand school in mid-50s, and it relates to the following geometric data. Let's consider a Lie group G and a compact subgroup K. Then the homogeneous space G mod K we will call Gelfand pairs if K is a compact and G is any. And if we suppose that this homogeneous space is not simply homogeneous but also symmetric space, then we can consider the space of Borel measures on this homogeneous space. And these Borel measures, they admit the convolution operation. So we have a convolution operation, and Borel measures transform in some star algebra with respect to this operation. And if we have these Gelfand pairs, then the space of Borel measures on the orbit, K orbits, because this compact sub.
It's broken. The connection broken.
Володя, we cannot hear you, and the image is frozen. Володя, I'll call him right now.
Wait.
he just lost connection. He's going to reload his computer right now.
Mhm.
It seems that connection problems are more serious than one expect. Let's wait for Volodya for a few more minutes. Mhm.
Гоша, ты дозвонился до него?
Sorry. Да-да, я сейчас как раз собирался это сделать.
Ага.
Ага. Ага.
Можно имейл послать.
Here's Volodya.
Я прошу прощения. I'm sorry. They did something. I don't know what they did. They wanted to, as usual. You know, всегда хотят сделать лучше, делают. Okay. А,
Виктор Степанович Черномырдин был гением.
Да.
Сказал одной фразой еще 30 лет назад.
Ладно, что-то инвариантно.
Мгм.
Ну,
Окей.
no. Риски спас. Окей. Окей.
It seems that you still have
No,
problems.
it is very strange. I say trust, and immediately everything stops.
Написано, что Владимир a commencé le partager l'écran, le partage d'écran, но мы ничего не...
Oui. Ну да, я понимаю. И я ничего не вижу. Вот что интересно. Если вы думаете, что я что-нибудь вижу, я тоже ничего не вижу.
Да. По-видимому, система меняет в BHS.
Что-то они меняют. Я не знаю, что они меняют.
Ну, я не знаю, лично я увидел пару новых формул для меня. И я не думал... вот, только появилась.
Неужели появилось?
Да, появилась.
Вот написано, что каждый cloud. Вот в этом
So I
дело.
don't know where I was stopped. I mean, I was
We
broken.
were speaking about Gelfand pairs and about the corresponding construction. So we have a group and a compact subgroup in it.
Yes, what I just repeat briefly. We have a group G and compact subgroup, and I remind that compact subgroup naturally acts on this homogeneous space. When this homogeneous space is a symmetric space, then the space B of X, which is a barrel measure space, can be supplied with so-called convolution of measure convolution. And this measure convolution transforms this barrel measure space in star algebra. In the case of X, such construction gives the group or construction, which is called canonical hypergroup, on the space of orbits of this action. So this action K on X gives on the orbit space barrel measures convolution operation. And with respect to this convolution operation, the product of measures gives you the product of characters. And these characters, in fact, they are Fourier images of measures. In the case of rotation group, which is a compact subgroup, and X is a R2, this construction gives you two Bessel, exactly, because these two Bessel can be defined with this generalized shift operator. So this operator, this is my two Bessel, and this operator defines the shift operator by this development of solution of this eigenfunction in this series. This is the usual Bessel. It's not my Bessel. That's why this minus. And then you can interpret this Bessel operator as the radial part of Laplacian on R2 in polar coordinates. And then the construction which I told you, like Gelfand pair, it's a construction which relates to the space X. The space X, which is just R2, and the rotation group X on R2. Then we can compute the corresponding measures, and these measures, so in this case, we have the one-dimensional sphere. We have this angle phi. As variables, we have u and v, and this is arc, which correspond to this small phi d phi. What I have in mind, I have this triangle. This triangle with side w square equal to y square plus v square minus 2 times uv cos phi. And then I want to make, in this construction of my Bessel operator, I want to compute the shift operators like product of eigenfunctions, which I explained you. This like a product of these two 0 degree Bessel function. Then this story, this I repeat you because I prepared it. I need to use my product formula, and my product formula contains this angle phi between u and v, and u and v, it's a length of these vectors. Length of these vectors. Then the length of this is w, and w we can express by cosine theorem, and the corresponding measure relates to dw. So we want to go from d phi to dw. We use this cosine theorem, and this cosine theorem gives you the following. You have this measure w dw divided by this. Sorry, I'm too quick. No, what I need to compute. Here it is. So my measure is a measure of this arc, this d phi divided by p. This is my arc. It's my measure mu, and this measure is w dw this divided by p times uv. It's comes from this because we replace w by this, and we should multiply this measure by character chi, and this character, it's a characteristic function. It's one if w is bounded by u plus v, u minus v by modulo. So it's a characteristic function of this interval. So our product in terms of this Cauchy integral can be written as our product in terms of this usual integral in R2 with this measure d phi replaced by w dv, and this expression, because we have also formula for area of triangle in terms of sine. You remember that we have this uv sine. So it's a double area. And from other hand, we can express this double area like in Heron formula like this. And then we have again Sonin-Gegenbauer-like expression, and our Heron formula gives another interpretation for this Kalin function. If we replace P by half perimeter of our triangle. So this square replacement of 4 degrees gives possibility to write the kernel in factorized form, namely like this. And the square root of this expression, it is 4 times area of my triangle. So this configuration we will call Heron configuration, and considering this like a conic, this expression like a conic in P2, we have the following description of this singularity locus. I remind you that it is a singularity locus in Landau singularity in the case of scattering amplitude with proper masses and Mandelstam coordinates. Anyway, now I will quickly go beyond what I didn't do last time. Now I take any n. It means that we have the following generalization of 2 Bessel. This one. So we have the following generalization of the connection and corresponding local system, which I mentioned, what Delin proposed in his approach to Weil conjecture. And what is interesting for this n Bessel case, that analytic solution of this Bessel analytic solution, which I denote GNX lambda. No, lambda, it is not very important. So it is again hypergeometric function, slightly degenerate because it's 0n hypergeometry. Usual Bessel n equal 2, and it was now it is 0n degeneration with parameters 1, 1, 1, and integral representation, it is exponent lambda and the following Laurent polynomial in parameters z, z1, zn. Of course, this Laurent polynomial should say you something about possible geometry, and this geometry, it's a toric geometry in the space, which is algebraic torus, algebraic torus of degree n, and such expressions are very important in the approach to mirror symmetry after given time. The measure, it is just a toric measure. It's a product of nz parameters and times dz1, dz n minus 1. So it is absolutely important that this solution, analytic solution of n Bessel appears also in the problematic of mirror symmetry. And we can ask what we can gain from this. Well, first of all, we can try to write the kernel for this and put this kernel in the game. And again.
Oh, just
Okay. No, no, it's okay.
Just
And
a small question.
so we want to consider the product of my solution in 2 points x and y, and consider the corresponding series in x and y. Also, this will be series with binomial type coefficients, but in some degree n, which correspond to our n index, n degree Bessel. And then we can again represent our product as a convolution with some kernel and this n Bessel solution. This convolution kernel we can write in homogeneous coordinates, so we can go to coordinates x over z, y over z, and then the corresponding function has this representation in terms of double series in big X and Y. X big, it's small x over z, and big Y, it's small y over z.
Sorry,
Then-
just to make sure I understand everything. Is it true then? So this Jn is solution of the n Bessel
Bessel,
equation because
yes.
the flat section of that connection.
For this connection, yes. It's an analytic solution, not K, because there are also singular solutions, but this is analytic solution.
And okay, I see. I really wonder how these formulas can be obtained.
What is interesting? That we can also to describe this kernel for n in geometric terms, like we did it for Heron configuration. We proved the following theorem, that if we take this kernel, let's denote it delta sub n of x, y, z, because it's function of x, y, z. So when we write this kernel, we can prove that this is the some symmetric polynomial. This symmetric polynomial starts with x to n, y to n, z to n, and it is always has different connection component. It is factorized in some typical component, which is 3 lines, x, y, z, and the component, irreducible component, it's a rational curve of degree n, which has n minus 1 and 2 times n minus 2 over 2 double points. And this curve intersect with this coordinate triangle lines in midpoints, like it was this conic in the case of Heron, but the equation of this curve factorize like this conic factorizes in product of linear terms, and here it is also factorized in product of linear terms, but coefficients in these linear components, they are nth root of unity. So if we have this equation, we can replace x, y, z by u to n, v to n, w to n, like we did it for Bessel. For Bessel 2, we have n equal to 2, so we have this degree 4 configuration. Now we have degree n configuration, and this degree n configuration can be factorized. And it is very interesting consequence.
May I ask a couple of questions?
Huh?
I just wonder whether you have twice the same result at that slide. Just is there any difference between the first and the second half of that slide? Because it
Where?
seems that it's just the same. The first statement of this theorem. No. That's in that slide.
It's a yes.
Yes,
It's a just how to say.
A typo.
No, it's typo because I made a copy paste, so I copy paste.
Okay, and then just what is what
The
kind of
statement is
what do you call the model here? What do you call the module? Just make sure I understand.
module, it's a corresponding connection and Bessel connection. And single locus of this demodule, it is this curve.
So you just consider the Bessel connection as a
Yeah,
differential
this one.
as a differential operator, right? You got it as a differential operator, and then a singular module, singular locus of differential operator is just this. So just not quite understand, not quite sure I understand this.
It is just a moment. I go back to show you this demodule which I showed you once.
Yeah, but what do you call the singular locus of differential operator of the module? I'm not sure I understand.
You want look, it is this.
So you just when
No,
you
no,
go
no, stop. I forgot. Where it is? Here. No. I showed you. I showed you.
you did actually. There was this drawing of a triangle with
Stop. Where it is?
a bit further.
No.
I'm sorry.
I remember that I showed you.
Yeah, you actually showed the drawing, but I'm not sure I understand the notion, the definition of singular locus of a.
Here it is. No, I that's what I want. Look.
Oh,
Here,
this equation, and the singular locus is.
this single point, you see?
Oh yeah, where just the points where the leading term vanishes.
Yes.
And that I see. It's just that simple.
Yes.
I see.
Very
I
simple.
see. Okay.
Okay.
Yeah. I see.
Yes. So as I probably I told you last time, but I repeat it again that these equations, I mean, for a different n, they are symmetric. You see, they are completely symmetric.
Sorry, could you show the previous slide again? The slide before this slide and previous one. Yeah, thank you. Thank you. Okay. Could you also again comment how did you prove this theorem?
This formula.
It's a purely combinatorial proof. It just manipulation with how to say. We had some computer experience and then proved by hand by induction.
These formulas, right?
Yes, this formula.
Oh, this one.
Yeah. We knew that it should be symmetric, it should be homogeneous, and then we had some few. You see, we have nice computations for small n, and then we understood that it is possible to.
Okay.
So it was very strongly inspired by Heron formula.
Okay.
Yes.
It's actually
For example, just you probably understand that this is just a product of x plus epsilon y plus epsilon square z times x plus x y plus epsilon z plus some plus times x. I should write somewhere minus probably minus x plus epsilon, where epsilon is a cubic square root
cubic root of unity.
Yes. This and then this guy is also very nice. This what we call this corresponding degree of our new variables, the Kummer pullback. So this is our singular locus, and to prove that it is factorized, we go to this initial times we go to some degree, so this Kummer pullback, and we have this. And this is not just occasional, because if you consider this locus, you can recognize that there is behind of it there is a interesting configuration of 16 lines in projective plane with coordinates u, v, w here. And I forgot how it relates, this configuration of 16 lines, it relates to some Kummer-like surface. Anyway, it is some singular K3 behind all this. Okay, it doesn't matter. This I told you that it is just a convolution operation. You can represent this. Now we want to look what's happened with these formulas if we take Clausen duplication, like it was in the case of G2 square. Now we have Gn square. And Gn square gives you, again, interesting series with binomial coefficients in degree n. And then we can interpret this operation, I mean this Hadamard convolution, we can interpret it like a convolution with the kernel. So we can write this square also in integral form and as a convolution with our kernel. So it means that in our function h x big, y big, we should put this diagonal x. But also, I didn't say about it, we can consider not only diagonal, but we can consider any slope. And we obtain a family which parameterized by this slope, and then the corresponding solutions gives you the family of these Laurent polynomials in the space, in the toric space, and it gives you some new examples of Landau-Ginzburg possible period functions. Okay, this is what structure constant in sense of Kontsevich and Dodesky. As I told you that we can generalize now this notion of structure constant for any algebras, just for the case of say generating function with polynomial coefficients. Let's suppose that we have some generating function phi sub lambda, f sub lambda. Coefficients of this function depends on lambda, and they are degree I polynomials. So it's a constant, degree 1, degree 2, etc. And we suppose that the first polynomial degree 0, it's 1, and then we can introduce the following algebraic structure: infinite product of two polynomials within indices I and j, like infinite sum of some structure constantCijk, and this is a case polynomial. So in terms of our multiplication kernel, this structure sum can be written very explicitly. So it is Dodesky and Kontsevich who proved this lemma, and this observation gives also
Volodya.
Yes, I'm unable to.
Experiencing other net problems.
This observation gives possibility to generalize all construction, not only for one accessory parameter, but for any number of
May I
accessory.
ask a question?
Hmm?
Of course, may I ask a question? Because of course we can consider this kind of generating functions, and these and k both they exist, but I wonder whether they are actually functions or they're just formal power series.
Formal.
Just
It's
formal.
more
So
formal.
this equation of Kontsevich and Adesky is also formal.
Yeah.
Okay. That makes sense. Okay.
It makes sense, and you can do it informally if you precise some details. For example, you precise the ambient space and topology and metric and say Hilbert space structure and so on and so forth. And then it will be reasonable to ask about non-formal convergence and so on. But even in this case, it is possible to write for our Bessel Gn generating function gives you this generating function approach gives you the following answer for the kernel. You see, it's our binomial coefficients in degree n, and here our non-homogeneous coefficients. So x over z and y over z. You can.
So what polynomials give you this kind of binomial n-power binomial coefficients in a structure constants a la Adesky and Kontsevich? What polynomials we should use to get this formula 13 as the generated function?
We did not use these polynomials. We use our.
So they did not. They not. Of
It
course,
is just no. We just use this. That's all. That's what we use. This one.
Just J. Just
Yes.
J.
This,
So of course, I mean, of course, every series of every set of polynomials with its property gives you some kind of.
we know from one hand side we know that the kernel is this series. From other hand side, by Adesky and Kontsevich, we know that multiplication kernel, if there are some polynomials, I don't care. They look like this.
Yeah, I just wonder whether you can actually find some polynomials that would give.
Yes,
you...
it's a back product. It's a back question. How to say inverse question? We can
Reverse,
yeah, we can do it. So this is the theorem which gives you the idea how this n's Bessel relates to some hypersurface in toric space in this product of spheres. So it's algebraic torus of degree n-1, and you have in this product of n-1 spheres, you have the following hypersurface, which parameterized by x, y, and z. And x, y, and z is our variables. And then if we consider such Landau-Ginzburg type Laurent polynomial, then we have this surface. We can consider the Poincaré residue, and it is exactly the case of our solution for n Bessel. This it's a theorem. This nothing to comment. First, we have this hypersurface. We start with this. Then we can consider the Cauchy or Poincaré type residue. we obtain some function of parameters, and this function is homogeneous, and series for both coincide. So we have a series for this function, and we have series for our kernel, and we have the same answer. And this is not
y1 through yn are just coordinates in this
yes.
gn minus 1. Oh, I see.
Yes. Now I can go again back. How? Because it looks very strange that initially different objects coincide, but it is not strange if we consider the more wide context. And let's consider the more wide context, which is so-called Calabi-Yau differential operators. These Calabi-Yau differential operators, they became very popular at the end of 80s and early 90s. What they are, Calabi-Yau differential operators. It's a monic operators of the following type. So we have this Euler derivation with t dt, and we have a set of polynomials, degree I each. So we have pi, it's a degree and polynomial in theta. So we have these polynomials which depend on variable t, degree n, with coefficients 1 in front of theta n, 2n. And we say that these polynomials have Mum point. It means Mum property. Mum property, it means that the origin t equal to 0, it's a point of maximally unipotent monodromy. I will explain in a few seconds what does it mean. And then what the origin of such polynomials? Geometric origins is Calabi-Yau varieties. Let's consider a family parameterized by T of Calabi-Yau n-dimensional varieties. T is a parameter on P1. On each variety from the family, we have n, 0 form, omega sub T, up to scalar. It is a unique holomorphic differential volume form. And from the theory of derivation by parameter or Gauss-Manin connection theory, we can consider the following functions, which we call period. These functions, they are integrals of my canonical omega t n form over different cycles. So we have these integrals, have these functions, and it is known that these functions, they are solutions of very special class of equation, which they call Picard-Fuchs equation. Now I want to show some examples and some explanation. First of all, what is a maximal unipotent monodromy? As I told you that there is this Frobenius method of solution. So if you have n order differential equation, then it has a fundamental basis n solutions, and these solutions, fundamental solutions, they are locally have the following type. If you have in the origin Mum point, it means monodromy matrix has only one Jordan block of triangle type. So it's upper triangle matrices, all such monodromies with Mum property, and it is a unique Jordan block with unity on diagonal and exponential denominators in upper triangular subdiagonal 1/2, 1/3, up to size of the matrix 1/k factorial. So if we have this condition, then we can write local fundamental solutions as a combinations of logarithms, but not necessary logarithm, because if we have this condition that the zero first member of this fundamental solution basis, phi 0 has no logarithm. It is just an analytic function which starts with 1. But other solution might have a logarithm in this situation. Okay, now what about the Calabi-Yau operators typical examples? The simplest Calabi-Yau variety, it is just an elliptic curve. In the Legendre representation, it is just this elliptic cubic with parameter t, and holomorphic differential being integrated as a function of t satisfies the following second order Picard-Fuchs equation. So this well-known Picard-Fuchs equation for this period of torus. For n equal to Calabi-Yau, it's a K3. For example, we have a family of quartics. This is a quartic which usually called dwarf quartic. The parameter t is a coefficient in front of the product, and the corresponding Picard-Fuchs equation has the following form. It is theta cube f, and the product 2 times theta, 4 times theta, 4 times theta plus 1, 4 times theta plus 2, etc. So this very special Picard-Fuchs for dwarf. For n equal to 3, again, we can consider such a threefold with a special Hodge romb, and Picard-Fuchs equation has a degree 4. And this Picard-Fuchs looks similar to Picard-Fuchs for K3, but degree 4. And this part starts with 5 and theta. So you see, there are not any this.
So this theta is just the operator you considered earlier, right?
Yeah, it's just examples, and examples of the corresponding operators. Now, why it is people was interested in this? People was interested in this because there is a paradigm of mirror symmetry which was proposed by physicists Candelas, De La Ossa, Green, and Parks in '91. They consider just a mirror pair of Calabi-Yau manifolds, and for this Calabi-Yau manifolds, they took for one of these models, they took this dwarf quintic with this Picard-Fuchs equation, and what they consider, they took analytic solution of this equation. You see, it's a very nice hypergeometric solution, which in some sense looks very, very simple, but it is the most interesting property of this solution, that this solution has integer coefficients. It's not only analytic, but it is integer. Then we take this other next member of fundamental basis, and as I explained, this term contains logarithmic term. So we have our analytic solution times logarithmic plus some other solution, which is no more good. This solution has no integer coefficients. These coefficients, they are rational and they start with t. They evidently denote, they evidently has 0 in origin. But it was a very, very famous and beautiful observation by Yao and Liang that if we take the first analytic solution and this logarithmic solution and take the ratio phi sub 1 over phi sub 0 and take exponential of it, then we obtain new function q. And this function q starts with t, but coefficients of this series is again integer. This was very surprising for Liang and Yao, and they proposed the following. They took this starting with t series with integer coefficients, this one, and they took it like a new coordinate q. They called it mirror coordinate or canonical coordinate, and they inverted it. So they consider this t as a function of q. And t as a function of q is no more integer. It starts with q, and then the next terms which start with cube, they have rational coefficients. So we can rewrite solutions of our Calabi-Yau or our equation of degree 4, this equation, we can write now in new coordinates, in this new coordinates q. So we had this old phi 0, phi 1, phi 2, etc. And then we can, instead of taking ratio in terms of t, now we take ratio in terms of q. So phi over phi 0, 1, phi 1 over phi 0, it's log q, phi 2 over log phi 0, 1 over 2 log q square, plus, and then you have coefficients which are no more again integer.
So phi k are just the solutions of this equation, right?
You have 4 solutions from.
It's degree 4, right?
We took just 3, for example.
Mm-hmm.
But if you want, you can write phi 3 over phi 0 as well. It will have a more logarithm, more degree of logarithm.
Okay.
And you see that this ratio, they are no more integer coefficient ratio series in terms of q. But, and it was also in the paper of Liang and Yao, they did it not for nothing. They said that if we take, instead of t over dt, if we take q over dq operator in square and apply to phi 2 over phi 0, then we again obtain integer series, integer coefficient series, which they called Yukawa coupling. In fact, it is not immediately evident how this integer series relate to Yukawa coupling, but relates in fact. It means it is really related to the deformation of cup product in quantum cohomology. But this is another story. I will not describe it. So if we take this Yukawa coupling series, then we write it like this, and then they propose to develop it. It is a very famous number theoretic hint to use instead of usual series, so-called Lambert series. It means that you take this instead of degree of the variable, you take this variable divided by 1 minus q to k, q to k, 1 minus q to k. And this, you have some coefficients. And these coefficients, again, if you multiply it by d cube, then they again become integer, 5, 2875, etc. And these are what they called instanton numbers. The importance of these instanton numbers is because they coincide with very famous numerological invariants. Physicists called them Gopakumar-Vafa invariants in genus 0, and it was known that Gopakumar-Vafa in genus 0 can be expressed in terms of Gromov-Witten invariants. But integrality of this Gopakumar-Vafa, it was not before evident. From this computation, they proved the integrality, and then they proved that this integral Gopakumar-Vafa gives exactly the Gromov-Witten invariance. Why? Because they recognize that these numbers coincide with numbers of degree d rational curves that pass on that lie on the generic threefold of degree 5 in P4. This is what the corresponding Calabi-Yau with this operator, this one. So we have this threefold, and this threefold degree 5 in P4 gives you the classical numerological problem of counting rational curves given degree d. D is this coefficient in this Lambert development. So the situation was amazing. The first two such numerological invariants, they were known. Of course, classical case, it was number of line, and number of line, it was Schubert who computed its number 5. And then number of conics of degree 2 rational curve was computed by Sheldon-Katz. It was 86, and Sheldon-Katz also computed it in 96, so 100 exactly later. And then, of course, the most important was this third number, because physicists get it from this hint, and mathematicians 2 years later, Ellingsrud and Ströme, they used equivariant localization formula. They computed this Gromov-Witten invariant for the next case of cubic curves. So it was conjecture, confirmed conjecture. The theorem, this conjecture became theorem in two independent proofs of Giventhal and Lian Liu Yao, and they proved independently that it is indeed the fact. And this was the famous mirror theorem. So in one hand side, in one mirror side, you have this Gromov-Witten invariant. In other mirror side, you have this instanton numbers, which comes from Yukawa coupling and this fantastic computation of differential equations. So this is what physicists were inspired in early 90s. So they decided to study Calabi-Yau differential operators, and they asked mathematicians to classify it. Now there is a huge database of these operators. This database is governed by Duke van Straten, but a lot of computations were done by Gert Almquist. He died a few years ago, and also by Van Enkevoort and our Vadim Zudilin, who is now in Netherlands as well, but he's from Moscow University, very good number theorist and analytic number theorist. So they have a huge database of Calabi-Yau operators. For degree 4, we will say that we have Calabi-Yau if all singularities of these operators are regular. Then we suppose this important property that in the origin the monodromy is maximally unipotent, so it's only one Jordan block. And then we also it is also in the definition that conjugation of Calabi-Yau coincides with itself. So it's a self-dual in this formal conjugation. And also, the most important, that we have the following integrality condition. The holomorphic solution, which comes from this Moon property, is always integer. The mirror coordinate, it means that if you take the ratio of the first two solutions and the exponential of this ratio, then it is always integral. And moreover, if you go to mirror map and you re-express in terms of Lambert series, you obtain again integer instanton numbers. So if we have this set of conditions, then we say that we have an equal to 4 Calabi-Yau differential operators.
So this ND is fixed for all, or
Sorry?
just ND, this instanton numbers, are they same for all such operators, or are they individual?
It depends which degree you consider.
So for operators of the same degree, they're actually all the whatever operator you. It seems that we are losing our listeners, attenders, because Dries Milga is leaving, I think. He left the chat.
Well, what I wanted to tell you, extra things, I wanted just to tell you that we can do the same with our Bessel operator. I just want to say that if we take our Bessel operators and we consider the operators which annihilates our kernels for Bessel, then they have the following property. First operators for first n, they have Moon property, and the Jordan blocks, they have Jordan blocks of size 2, size 3, size 4 with 1, 1, 1 over with 0, 0, 0 on the diagonal. But if you take degree 6, then you have catastrophe, and you have the second Jordan block with 1 on the diagonal and times 1 times 1. It's one extra block, and then you leave with 2 blocks on the size of the block. So
what operators do you take? What operators do you take?
This is a kernel for Bessel.
Ah, so you just
But I called it Calabi-Yau-like because they are not Calabi-Yau. And this, I'm speaking about,
you just take the kernel and you look for the operator.
yes, I take Calabi-Yau, I take this Bessel, and I compute operators, Fuchsian operators, which annihilate the kernel.
Are they uniquely defined, these Fuchsian operators?
Yes, you will see.
I'm not sure.
So this operator for 5 Bessel. It's for 5 Bessel, it's K5.
Just how do you compute it? Is there any
By
given-
computer,
just okay, just write down it in
yes, by computer.
Just write down the general coefficients, right?
Yes, and this is the Picard-Fuchs operator, which annihilates this 5 Bessel kernel. You remember that I showed you this. You asked me what is the module singular loci.
Yeah, single locus here is just
It was first order.
coefficient at D4, right? Here the same.
Yes, here it is for 5. It's only one operator for 5. I didn't pass other operators because for 5 it is the last one for which we have the mum point. You see, so we have this degree 4 differential operator. This is a singular locus. This is a singular locus, and this singular locus, we can show that this singular locus is exactly can be rewritten in terms of this configuration of Heron type. This one. So this is a Frobenius basis for 5 Bessel. So this is analytic solution. This is phi 1. This is phi 2. And you see, this is the integer. This is not integer, but mirror coordinate. Again, integer. Again, like it was for Calabi-Yau. And mirror map gives you this integer. UCAL coupling can be right in non-integer form, but if we go to a Lambert series, it's a mistake. It's I3 it's a misprint. It should be not in denominator. It's like it was D. You see, and we have again integer instanton numbers. So this operator behaves like Calabi-Yau, though it is not Calabi-Yau. But for n equal to 5, it is still.
Do you have any interpretation of these numbers?
No, we don't know. That's a question. But it should be some numerological. But these numbers are unknown in OEs.
That's interesting. That's
We have many experience with this slope. We change the slope and compute different how to say different data and compute different differential operators, different numerical and some of these numbers, they are known in OEs, but this instanton numbers, they are not known. It is interesting.
not in the encyclopedia of.
No, we should write about it to this encyclopedia.
So you said that this is not a Calabi-Yau operator exactly because these instanton numbers are unknown.
No, it is not because they are. We consider only operator for 5 Bessel, and we speak about the family of Fuchsian operators. So this condition satisfies only regular singularities. We describe the operators which annihilate K to N.
Yes, but why is it not Calabi-Yau? You said it's not Calabi-Yau. Why?
Because only well, because we didn't find it it should be in the list of Duco, and it is not.
So it is Calabi-Yau in the sense of your
Maybe it might be-
definition.
Maybe no. If we extend the definition that we can call this Calabi-Yau-like operator, because in principle, you see, it is in principle Mum point, because it's only
No, I just want to understand, is it Calabi-Yau in the sense of your definition above?
in the definition above, it's Calabi-Yau, yes.
Yeah, but you told that it's not
But
Calabi-Yau.
we suppose from the very beginning that all of them are Calabi, but not. This
Yeah. Again, with
I
number
just
six.
don't understand. Okay, I understand. But so it is Calabi-Yau in the sense of your definition,
yes.
but it is not Calabi-Yau in the sense that it is not in the
We
list of.
don't know. Well, first of all, it is not Calabi-Yau because the period, it is only Landau-Ginzburg. We don't know if it is possible to for n equal to 3. This is a real Calabi-Yau. This is real
Okay.
Calabi-Yau.
Okay.
Because this period of this for n equal to 3, it can be compactified to Calabi-Yau. So it's this historic variety which I showed you. It can be compactified like but it is a Fano. Kind of.
Okay.
It's a Fano with Greenstein singularities. If you blow up this Greenstein singularities, you get Calabi-Yau.
Mhm. So the
But
manifold.
for 5, we don't know.
The right
It is not known. So it's not
It
known.
is not
but
known. It is not what is not known. It is the formula operator is Calabi-Yau. What the question? If there is a Calabi-Yau behind of it, it means that if there is a real Calabi-Yau threefold, threefold, it's a degree 4. So it's a threefold. If there is a threefold for which some
I see.
It looks like a dwarf like, but we didn't prove that it is possible to blow up and to compactify to Calabi-Yau. So
Okay.
maybe
it's a good question to Przhalkovsky.
Przhalkovsky said that it is. He said that it is just he. You know, I gave the 2 hours talk in Shvarevich seminar. And Przhalkovsky was initiator, and he said that, well, it's in the Bondel also. The Bondel said that it's understandable. It's just
so they said that it is Calabi-Yau, right?
Yeah, they think it's just a technical questions for them.
Okay.
Algebraists, they always like this. Okay, thank you very much. It was a very interesting talk, actually. I learned a lot.
Can I ask one more question about these Calabi-Yau operators?
Yeah.
Is it true? So is it true, or maybe is it known that the differential operators are common factors of some commuting ordinary differential operators, which are holomorphic? Is it known or not?
For me, it is unknown. For me.
Okay.
For me, it is unknown.
So what do you mean? Why do you think they are factors of some commuting operators? I don't quite understand.
No, because the factors behave very similarly to them. That it's natural question.
What factors?
Factors of commuting ordinary differential operators. Common factors of them are regular, etc. So really, well.
I see. Okay. Thank you. It was very, very interesting talk. It's a pity. Yeah, we actually, I think it is worth to have a kind of mini course on this subject. And of course, this mini course should be attended by Vitya Przhalkovsky to have his comments.
No. I suppose that Przhalkovsky perhaps has his so-called hand compactification. Maybe he mentioned exactly this one, that he can just compactify it to the toric variety.
Yeah, to something he knows.
I think that for all of them, these equations of Bessel type, they are too simple, and
so how many terms do they need?
they don't care about this because And it is the same story with Maxim and Odesky, because they wrote a huge paper about this multiplication kernels. They classified some old hypergeometric multiplication kernels, but they just didn't draw attention to this Bessel. They said, okay, there is a Bessel, okay, just.
Mhm. Okay.
Yeah, I
Thank
see.
you very much.
Thank you very much. So thank you.
Anyway,
It's already quite.
we hope just in a couple of maybe in 1 week put it in archive the short paper with Luca and Ilya, maybe. And but it will be only about this numerology, about this kernels of Bessel and
Okay, I think it's time to stop now. I'm sorry. I mean, it's more than 2 hours long, and you have.
okay.
I'm
Yeah.
sorry, but it's actually very interesting. It would be nice to have a series of talks, not just about Bessel, but also about mirror symmetry. I just wonder whether we can invite somebody to talk about mirror symmetry from, not from numerological point of view, from.
No, it's a part of the Maxim homological
Yeah. I really wonder if it is possible to invite Maxim to us, but I don't think he will agree. He's too busy, probably.
Well, he is busy, but he always very kind, but he always speaks about what he wants to speak.
Yeah, precisely.
Who? Maxim Kontsevich?
Maxim.
Ah, yes. You
You can't ask him to speak about homological mirror symmetry because he said, "Oh, it's."
Yes.
So maybe you can ask maybe Sasha Polishuk. Sasha can tell about it.
Okay.
Oh,
Sasha,
yes. But
you can ask Sasha.
if he will agree, of course. I think it's much easier to invite Przhalkovsky.
Кстати, Przhalkovsky, why not? Video very clear.
Yeah, he's quite clear. But
And
also,
I'm not sure if Sasha Polishuk will agree. It's very
Sasha
difficult.
Polishuk will agree, but Sasha Polishuk is very far. And,
Yes.
even if he's in Europe, he's very busy. That's the problem. You can ask Sasha Polishuk to tell about elliptic algebras. They have very good new results with his Chinese student and with Nikita Markaryan. It is really new breakthrough in Odesky field in algebras. What I told Gosha maybe knows because I talk about this Q5 algebras in conference which Buchstaber and Mikhailov organized in Grozny. And then after I didn't want to publish this because it was just partial results, but Buchstaber insisted and I published in this book, which they published with Mikhailov. And then Polishuk and Nikita Markaryan, they reprove some things from this because they were inspired, the questions which I left. It is interesting. It seems interesting. And probably Markaryan, you can ask Markaryan. He can tell you.
where is Markaryan, by the way?
In Strasbourg.
In
Strasbourg. He will be next year in Strasbourg.
I see. Okay, thank you. In any case, thank you very much. I really love to know more, but maybe next time.
Okay.
There's somebody who can talk on this. We'll probably try to invite. But for now, it's time.
You can ask Ilya. Ilya can tell you more about the computer side of this story.
Yeah.
Okay.
Gayur. Okay.
Ilya can tell you more.
Okay. Thank you. And so next time we'll probably invite Sasha Chervov to talk on something. He wanted to make a talk here.
Sasha, if you can ask Sasha can you ask him to tell about this Cartier-Poata and this his conjecture, new conjecture about topological growth, and it is interesting.
Sasha has always had very
It was
interesting.
the question no mat overflow. But
Well,
he
he had
had
very interesting questions, Sasha. It's one of
Uh,
his definitely.
Gosha. You can ask him to tell about causality and Cartier-Fuata condition. That's
Okay,
interesting.
he had some idea what he was going to talk about, so I don't want to insist, but if he is free to change or free to choose, and I'll definitely use your advice. Okay, thank you.
And he can just put many open questions about Manin matrices, about Cartier-Fuata, about this. I don't know. It would be interesting. I would be happy to hear him.
Okay, thank you, and bye-bye. See you next time.
Bye.
Володя, тогда, когда вы сможете, там, в четверг, напишите мне. Хорошо?
В четверг, я не знаю, мы
Четверг, пятница, суббота, когда у вас будет время.
Ну, вот мы с Ирой должны там закончить все это. Я надеюсь, вы что-нибудь завтра закончите, а послезавтра?
Да. И в четверг, в пятницу или в субботу можно будет тогда обсудить,
Да.
вот, который
Да. Ага.
когда у вас будет время. Всего доброго.
Пока.
До свидания.